will talk about this exam. This exam is not, it doesn't look good.
Yeah.
3, okay? So I will see. If I made any mistake, I will go over. If not, I will maybe consider something, okay? Let me first see, because sometimes the counselor made a mistake, or sometimes when I graded your paper, because I don't see many of you who really didn't do good this exam, honestly. Okay?
What about next week?
Next week.
Next week. Are we going to have a study guide? Because I feel like when I study and when I look at your questions on the quiz, for some reason it just don't click. Or I
Okay.
don't know if it's like.
Are you saying that whatever is not covered on the PowerPoint is not on the test? Are you sure about that?
Like the way I study in the PowerPoint, I'm looking at the questions. I'm just, I don't know, they don't look the same to me from what I'm learning in the PowerPoint.
Can you pick an example? Like the questions, I
If I
have the
had
test
task,
with
if
me.
I had the actual task, I could like.
I have the test with me. Maybe we can discuss about later on. I'll give you the question and then I can show to you. And if there are any things that we never covered, then okay, I accept your comments. Okay, let's see. Let's see which test, which questions, yeah, that was not covered, and then we can discuss. I mean, by the way, this test, I don't know. Most of you didn't do well with this test, so maybe you're right. I don't know. Maybe repeatedly saying what will be on the test. This is what I'm thinking, that you guys as a chemistry 103 students, as a future nurse students, that you need to know about some of these. Like, for example, attraction forces. Attraction force between molecules. You need to know about London dispersion force. Now, here is the trick, okay? London dispersion force. All molecules experience London dispersion force. Okay. 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 Here. Okay. We are hydrogen bond. I already explained about hydrogen bonds, right? Hydrogen bond is a bond between hydrogen atom and oxygen, nitrogen, and fluorine. Okay. It's a bond between oxygen, nitrogen, and fluorine. That is a hydrogen bond. And what is important in hydrogen bond? Hydrogen bond is the strongest of all. When I say all, we have 3 actually. I don't know why, but it's supposed to be 4. But we have 3. Okay, doesn't matter. We're not going to add anything. London dispersion force, dipole-dipole force, and hydrogen bonding force. So if I give you a choice on a test, which one has the strongest force? A hydrogen bonding is the strongest one. Next, a dipole-dipole force. The weakest of all is what? London dispersion force. How does the London dispersion force comes? By the unequal share or unequal distributions of electrons or asymmetrical distributions of electrons. So it is the weakest. There is a force, but it's really can be easily broken down. Okay. Also, there is a logic comes between behind those bonds. The melting point and the boiling point is higher sometimes. Okay. If a substance has higher melting point or higher boiling point, the implication is that the bond of attraction is stronger. Okay? So if a substance has only London dispersion force, if you compare the substance with another compound that has a hydrogen bond has a higher boiling point. Helium, for example, the boiling point of helium atom is going to be 50 or sometimes below 0. Okay? The boiling point of water is 100 degrees centigrade. Okay? So the reason why is that because helium has a London dispersion force. Helium has a London dispersion force, but water has a hydrogen bonding because hydrogen bonding is stronger. To break up the molecules of water molecule, you need a lot of energy so that the boiling point of water is greater compared to helium, which has a London dispersion force. So in the choice, for example, maybe they will ask you, which of the following substance has a higher boiling point? And then they will bring you water, for example, potassium chloride, helium. Okay, now these 3 elements, which one has a higher boiling point, you think? A higher boiling point. No. If I have helium, water, potassium chloride. Potassium chloride. Potassium chloride. Okay, if it was between water and helium, it is going to be water. But if it was between potassium chloride, water, and helium, potassium chloride comes first, then follows by water, then follows by helium. Why? Potassium chloride is ionic bond. What's ionic bond? It's a very stronger attraction. It's a different charged bond. That's between plus and minus. There is the best bond. I mean, always hydrogen bonds are the strongest regardless. Then comes hydrogen bond. Then comes, we don't have any choice, but then comes dipole-dipole bonding. Then finally, the least bond that we have is London dispersion forces. Okay? So that's what I want you to get the concept of that. So here, for example, types of force, we have London dispersion, relative strain. The relative strain is weak. Weak. And now, again, I don't want to trick you, but it is all molecules, regardless, all molecules, if it is ionic bond, if it is molecular bond, if it is whatever bond, all molecules exhibited London dispersion force. They have London dispersion force. Is that true or false? Is London dispersion force belongs to certain atoms, certain molecules, or all molecules experience that? Just general concept. I'm sorry? No, it is all. Yes, all molecules, all substances. Think about this. Ionic bond, say for example, there is an ionic bond, is a bond between potassium and chlorine. Potassium chloride experiences ionic bond, big time. We know that, right? Ionic bond. But, are there electrons in potassium? Are there electrons in chlorine? There are electrons, right? Behind the bond of the ionic bond, behind that bond, still there is a London dispersion force. There is unsymmetrical distributions of electrons. However, that London dispersion force is not that much vivid. It's not that much shown. You know, you can't see it, but there is. So all molecules, whether they are molecular, whether they are ionic, all molecules exhibited London dispersion force. Okay? But you can see, for example, dipole-dipole bond is molecule with a net dipole attraction. Okay? Hydrogen bonding, you can see hydrogen bonding only with what? This is what I want you to remember. A hydrogen bonding is between oxygen and hydrogen, or between nitrogen and hydrogen, or between hydrogen and fluorine. That's it. Three things. Okay? I may say, because I like trick sometimes.
I know, that's the
Okay, I don't like trick at all. If you have hydrogen and sulfur, for example, a bonding between hydrogen and sulfur, is it hydrogen bonding?
No.
Unfortunately, no. You see, because hydrogen bonding is a bonding between hydrogen and oxygen. Okay, a bonding between hydrogen and nitrogen. It's a bonding between hydrogen and fluorine. That's it. Okay, three bonding will be enough. Okay, now let's define it. What is a boiling point? What is a melting point? Boiling point means the temperature at which a liquid is converted into the gas phase. That's what the boiling point means. Melting point is the point at which a solid is converted into a liquid, right? That's what we call melting point. The point at which a solid is converted into a liquid phase, we call melting point. This is what I said earlier. The stronger the intermolecular forces, always is the higher boiling point and higher melting point. It is absolutely true. If it is stronger molecular forces, then it's going to have a higher melting point and a higher boiling point. Yes?
Is hydrogen bonding stronger than ionic bonding?
No. No. Ionic bond is the base. Yes. Okay. Yes. Ionic bond is the base. And then comes hydrogen bonding. Then comes dipole-dipole bonding. Then comes dispersion, electron dispersion forces. Okay? Now, here is a good example. This is a comparison between methane and water. Methane is an organic compound. It is a natural component of gas. And methane, the only force that's experienced is a latent forces only. And you can see this is not something that is written to make you happy, but this is experimentally determined numbers. The boiling point is less than 0, -100, because there is a weak bond. You don't need to apply a lot of energies there. The melting point is low. What happens with hydrogen bonding here in water? Water experiences hydrogen bonding. Compare the boiling point versus with the boiling point of the London force is 100 degrees centigrade. The melting point is 0 degrees centigrade. The reason for these two compounds is going to be what? The reason is the intermolecular attraction. One has a London dispersion force, the other has hydrogen bonding. Okay? Both propane and butane have London dispersion forces and non-polar bonds. Okay. Also, another point that have we discussed something about organic compounds a little bit last time? Organic? A while ago. Okay. Well, maybe last time because you're not here. But we're discussing it, right?
We discussed about butane.
Okay, alkanes. What is alkane? Alkane is a saturated hydrocarbons, right? Have we discussed about alkanes?
No.
Okay, let me explain a little bit. And then we can have some ideas what organic compounds means. We have okay. We have a group called alkanes, okay? Alkanes are saturated hydrocarbons, okay? Saturated means if something is saturated, just in the word of saturated, what does saturated means? Enough amount, right? It has excess amount. Unsaturated means there is a deficiency, okay? Now these members here, what you see, propane, butane, ethane, they are saturated hydrocarbons. In other words, they have enough hydrogen atoms to be partnered with the carbon atoms. That's the whole concept of it, okay? Like the first 4 or 5 members of, like, this is called methane. This is called ethane. Now notice here that in the name, they are ended with A and E. That is where the alkanes family are. All alkanes are ended with A and E, okay? We have something called propane. It's this guy right here, propane, okay? C3H8, that's propane. We have butane. We have pentane. What do you think hexane will be? How many atoms hexane? 6. Hexane will be 6. Hexane, heptane, octane, octagon, heptagon, pentagon. This is a big word like numbers. They refer you numbers. Okay. So I have, for example, C6H12. No, C6H14. That's going to be hexane. Okay. Now, you don't have to really memorize this. Sometimes you don't have to. There is a formula for the alkanes family. Alkanes can be written as CnH2n plus 2. If you remember this, you don't have to memorize this. What's this? CnH2n plus 2. N refers to the number of carbon atoms. Okay? Say for example, if you have 7, C7, how many carbon atoms you have?
7.
If you have C7, how many carbon atoms? 7, yes. How many hydrogen atoms you have?
16.
16, yes. How do we know that? 2 times 7 plus 2. So it's going to be C7 and 16. It's going to be heptane. Okay? Now, it's easy, right?
Yeah, when we put it on wood, we can go, we get
Now, okay. Okay, these are the saturated hydrocarbons. Okay. These are the alkanes. Okay. All of them have a suffix of ane. Okay. All of them have organic compounds or hydrocarbon compounds because there is only hydrogen and carbon, right? And the type of force, these are molecular compounds. Okay. Now, the type of force, intermolecular attraction that they experience here is going to be a London dispersion force. Because there is no like ionic compound here. There is a molecular compound here. Yes. No.
What's the formula?
If you know the formula, that will be enough. Okay. If you know, but one thing that I want you to remember is what type of, now let me bring this issue here. What kind of intermolecular forces or intermolecular attractions they will experience these kinds of forces? A London dispersion force. There is no hydrogen bonding here. Okay? Between each atom, they have a London dispersion force. And then the example is that London dispersion force is, you can see, is weaker. Now, another thing that I want you to remember, maybe, this is what I want you to remember. Maybe like, if I compare these two here, or compare these two here, between two saturated hydrocarbons, between two alkane families, which one has a higher dispersion force? Like, let's say if I compare methane versus ethane, ethane versus propane. Ethane has a higher dispersion force than this. The reason why for that, because the more molecules you have, the more atoms you have, the dispersion force is going to be up. Okay? Maybe for that reason I'm listed here. Okay? So that's one of the things that we maybe take into consideration. Okay. And then we have a process called endothermic and exothermic. Can anybody tell me what this endothermic process means? What is endothermic? When you do lab experiments, you heard about the word endothermic. Endothermic means if energy is absorbed to the system. Okay? Let's say that you have ice. You want to melt the ice. To melt the ice, what do? You what? You heated it, right? Heated means that's going to be endothermic process. It's going to be endothermic process. Okay? In other words, you're going to apply energy. You're going to apply energy. That is endothermic process. Anything that you involve or you apply energy is endothermic. And exothermic means when the system or the reaction gives you some energy. Okay? That means, for example, suppose you have a reaction. This is a simple reaction here. What's happening here? You have, by the way, this is zinc, metal zinc. It's a solid metal. Reactions hydrochloric acid. Aqueous, I put aqueous. What does aqueous mean? Water, dissolves in water. It gives you zinc chloride plus hydrogen gas. Gas is produced. This is a single replacement reaction. Okay? Now, this is a single replacement reaction. And also, this reaction, at some point, it produces energy. It produces energy. At least you can tell that it produces energy. If you touch the test tube, when you mix the zinc metal with hydrochloric acid, you can feel warmer. You can little bit feel warmer. That means the reaction here, it produces energy. It produces to you, to the surrounding, to the area. Okay? So we call this what? Exothermic process. Okay? All the metabolism, like say for example, if glucose burns in our body, this is a good example. Okay? We need oxygen to to burn the sugar, right? So that this gives you what? This gives you carbon dioxide and water, plus what? Plus energy. Energy to walk, energy to talk, energy to discuss, energy to study. Okay, energy to ride your bike. So you need energy like glucose plus oxygen. This is what? This is exothermic process. Okay? Okay? This is an exothermic process. So we have endothermic process, we have exothermic process. If you want to break up a molecules, you invest energy, the process is said to be what? Endothermic, right?
What's an example of endothermic?
Ice is a good example. You melt ice to make it liquid.
So is that because it's not a chemical change that that's that, or is that?
It's not a chemical change. It is you're changing the state of the substance. Like for example, you have a solid ice, and then you wanted to make it into liquid.
Oh, so you're
And
saying
you have to-
you're not changing the what it is.
No. The chemical composition remains the same. The state has to be changing. Because the chemical composition of water is water, ice is
Right.
water, H2O.
So you're not changing that, and that's the difference, because it stays water, and the endothermic, or the exothermic, you're actually chemically, right?
Well, exothermic is chemically changed, and at the same time, exothermic means that you make sure that energy has to be generated. That reaction has to produce some energy. Okay, that's what
And
exothermic
you can
is.
tell that it produces energy by heating.
Yeah, that's simply, yeah, you can say. You can even touch the case, or you can feel the warmth that produces exothermic process. But this we use in our daily life. Maybe in biology, you might learn like glucose or sucrose or whatever material burns with oxygen, produces carbon dioxide and water and energy. Chemistry, explain this, that this is a good example of exothermic reaction. Okay? Now here, this is a good example. Melting is an endothermic process. If you melt the substance, it's an endothermic. How come a substance can be melted? You have your ice cream. Leave your ice cream outside in room temperature. It's melted. Explain just to me in chemistry way. What happened? Why your ice cream is melted? Simple. It absorbs heat from the surrounding, from the room, right? And then it melts. Right? So this is endothermic process. This endothermic process. It melts. And it absorbs heat from the surrounding. Surrounding means room temperature. Maybe ice cream can stay with below 0, but room temperature is what? 25 Celsius. Freezing converts a liquid into solid. Now, if something is freezing, okay, that is the opposite of melting. Now the process is endothermic or exothermic? It's exothermic, unfortunately. It's exothermic. Now it's also another concept that we need to know here. The law of conservation of energy. If the same amount is absorbed in endothermic process, that same amount has to be removed, the same amount. Why? It is the law of conservation of energy. Okay? If I need 15 kilojoules of energy to melt a substance, during the process of freezing, the 15 kilojoules of energy has to be removed. Law of conservation of energy. Just like the law of conservation of matter. In the atomic theory, matter said that you start with X amount of substance, Y amount of substance, you react with X with Y, but at the end you get a new, absolutely new product. New product is formed, but at the end the amount remains the same. Nothing was disappeared, nothing was destroyed. The quantity always remains the same. The same principle, the same theory works for the law of conservation of energy. If you apply heat to melt a substance, the same amount of heat is going to extract or emitted when it freezes. It freezes because it absorbs to melt. When it freezes, it releases the energy. It releases that energy. So freezing is exothermic. It gives off heat to the surrounding. The amount of heat gives off the surrounding, the amount of heat that absorbed are said to be equal. Under what principle? Under the principle of energy, the law of conservation of energy. Okay? So you can see here, endothermic and exothermic is a good example here. Melting is endothermic process, right? And freezing is exothermic process. You have a solid water here. A solid water is melted into a liquid water. So that's endothermic. And a liquid water can be freezes. It can turn into solid. The process is freezing. But what is the reaction? The reaction is exothermic. Now, we have something called heat of fusion, a new word here, heat of fusion. It looks like a cozy word, but it's not cozy anymore. It's fusion. The amount of energy needed to melt 1 gram of a substance. If I have 1 gram of substance, if I need to melt that 1 gram of substance, how much heat I need, that particular heat is called heat of fusion. Just give a definition for 1 gram of substance. For 2 grams of substance, then I have to multiply that. Right? If I have 1 gram of substance, that's called heat of fusion. Or another word is heat of fusion. I think they have some more here. Heat of fusion means the heat that is used to convert a solid into a liquid. Okay? A solid into a liquid. That's called heat of fusion. When you have ice, you must apply some energy to change that solid into liquid completely. So that piece heat, that part heat, okay, just to convert all the solid into liquid, that part is said to be heat of fusion. We have something called heat of vaporization. Heat of vaporization. What do you think heat of vaporization should be? How you define heat of fusion is a heat that is used to change solid into liquid, right? Heat of vaporization will be a heat that is used to change liquid into gas. Very good. Liquid into gas. There is a heat. There is a piece of heat that we are interested in. Not all of the heat, but there is part-time heat, a part of heat that we are a segment of heat that changes the liquid into gas. That special heat, in other words, is called heat of vaporization. And there's another heat that changes all the solid into a liquid that is said to be heat of fusion. Heat of fusion. We have 2 types of heat: heat of fusion, heat of vaporization. Vaporization is the conversion of liquids into a gas phase. Vaporization is endothermic. Do you agree with that? Vaporization is endothermic because you have a liquid, you need to have more heat to break up all the molecules of the liquid to turn it into gas, right? So it is endothermic process. Condensation is the opposite actually. Condensation is the conversion of gases into what? Into liquid phase. What type of process is that? Endothermic or exothermic? Exothermic. Exothermic. If vaporization is endothermic, condensation is going to be exothermic. Yes.
What was the second one?
Heat of vaporization. Vaporization.
Heat of fusion. Professor, is heat of fusion the same thing as condensation?
No. All right, okay. Heat of fusion sometimes is written like this. Heat of vaporization sometimes it's like this. Okay, now what's your question?
Oh, I wanted to know the keys.
Okay, this is heat of fusion, this is heat of vaporization. Delta HF. Delta HF, you might see in calculation or you might see in some literature there is delta HF. Then what's delta refers to? Change, difference. H is heat. F is fusion. It's an abbreviation. Delta HV, difference in heat of vaporization. Okay? Okay, now, yes.
Can an example be for heat of vaporization? Could we,
A liquid water turns into a gas.
Okay, so you could use it like put in a refrigerator and then
No.
or it could be another.
Let me give you a simple example. Take water, 80 degrees centigrade water. What's that? If you have water at 80 degrees centigrade, if you have, huh? Water is hot. So water is hot. That's a good way to say it. So water is hot. Take water at 100 degrees centigrade. This is a boiling point of water. Take water at 110 degrees centigrade. Evaporate. It is gas. Now there's a transition. This is a transformation. Okay? From 100 degrees centigrade, we're not saying that this is the point at which water starts to boil. Starts to boil. In other words, water starts to boil means that you see the molecules are coming out. You see the bubbles coming out anyway. That is 100 degrees centigrade. Now, this doesn't mean that the whole molecules of water are turned into a gas level. But this means that the water molecule are starting to bubble up. Boiling point starts, but boiling point is not completed. There is delta HV, heat of vaporization, that changes the whole water molecules into gas.
So it's not liquid into solid, it's liquid into gas.
Of course. Heat of vaporization is between liquid and gas. Heat of fusion is between solid and liquid. Right? Yes.
So Professor, there are only two heats, right?
At this point, yes.
So for condensation, there is no heat required.
Well, condensation is the opposite of heat of vaporization. We change the gases into a liquid phase.
So I can say heat of condensation, right? There is no heat for condensation. That's what I'm trying to ask.
We have to have cold and hot in order to
Listen,
make
let me explain this to you.
So,
If heat of vaporization is 90 kilojoules, right? Heat of fusion is going to be minus 90 kilojoules. You understand? If heat of vaporization means you need to have 90 kilojoules of heat, 90 kilojoules of heat to change the liquid into gas, right? To condensate that, to make it into a liquid, how much energy is you have to give it off? Minus 90, the same amount. So there is no heat of condensation rate per se, but you take away that amount, in other words. If you need 90 kilojoules, heat of condensation will be minus 90. Taking away the same amount of energy away, and that is no. That is exothermic process. Okay. Yes. Kilojoules. Oh, kilojoules. Okay. Okay. You were not here last week. We discussed about that. What is kilojoules?
1,000
Kilojoules is 1,000 joules. Okay, joules is a unit that is used to measure energy. Okay, like temperature is measured in what? In Celsius, in Fahrenheit, in Kelvin, right? Energy is measured in what? How do you measure energy? Joules, calories, kilojoules. I don't know if I forget something. Big calorie, big C for food, for nutritional food. We use big C, right? CAL, right? So these are the units that we measure energy, okay? Please, if you don't understand anything, please ask me, okay? Because sometimes I may skip, sometimes I think that you already knew this, but some of the principles we need to know. So any questions you can ask, okay? Don't worry, as we can go over with that. So kilojoules is a unit for measuring what? Energy, okay? Also, 1 joules. Go to the PowerPoint, it shows you, if I'm right, 1 joule is 4.1, no, wait a minute, 1 calorie. 1 calorie equals 4.184 joules. This is also another unit that we have to learn. 1 calorie equals 4.184 joules, okay? Suppose if I have 15 calories, in how many joules it will be equivalent to? 15 times 4.184 joules per calorie. Okay? Because 1 calorie equals 4.184. This will be given to you on a test. You don't have to memorize this, but you need to know how to do the calculation here. Yeah, I'm not going to, I'll say 1 kilojoules equals 1,000 joules. I'll tell you that, okay? But you must do the mathematics, okay? Okay, now let's see. Okay, this is the same things that we have. Oh, sublimation. There is another thing. The process is, the solid has to be changed into a liquid if you apply heat. And if you apply more heat, the liquid has to be changed into gas. That's how it is. Solid goes to liquid, liquid goes to gas if you apply heat, right? Unfortunately, there are some strange things happening here. There are some substances, without having the liquid state, they move directly to the gas state. Why? I don't know. Don't ask me that why. But there are some substances, without having the liquid state, they jump into the gas state. Dry ice, dry carbon dioxide, something like this. They are not keeping the tradition. They are moving from solid to gas. We call them sublimes. It is sublimation. Sublimation means it's a conversion of solids directly into what? Into the gas phase. Sublimation is actually, it's an endothermic process, right? There's no question about it. It's an endothermic process, okay? In fact, again, just to think a little bit more, the heat of sublimation is equals to the heat of fusion plus the heat of vaporization together.
Say that again.
Okay. If we have what is sublimation? Sublimation means solid, the heat change of heat or the heat required to change the substance from solid to gas directly without having a liquid phase, no liquid phase. From solid to liquid, what is the heat needed? What type of heat is needed? Heat of fusion, HF, right? From liquid to gas, what is the heat needed? Heat of vaporization. Now, if I have from solid to gas, the heat needed is going to be heat of fusion plus heat of vaporization.
Does that mean that for sublines, their heat of vaporization is very high?
Heat of vaporization is always high. It's always high. Now, if you compare, that's another good question. If you compare just generally, if I ask you this as true or false statement, is heat of fusion or heat of vaporization is higher? Just comment thinking. What do you think? The heat of fusion or heat of vaporization do you think is more higher for any substance? It can be water, it can be ice, it can be ice cream, it can be anything. No. Vaporization is higher. Vaporization is higher. Why is that? You need more heat. Technically, what is to you vaporized heat? What does vaporization mean? What is that? Okay, yes, that is a definition. But what is vaporization? Generally speaking, what is the vaporization means?
Applying more heat to liquid gas?
Yes, that all molecules has to be broken down first of all. All molecules have to be broken down in order for you to turn into gases. All molecules. So it means that you must have a lot of heat. You must need a lot of heat. Okay? So because there is a complete dissociation of molecules. There is an absolutely completely dissociated molecules must be there. So always, regardless of the material you have, it's always true that heat of vaporization is always greater than heat of Fusion. Now, heat of sublimation is the result of heat of fusion plus heat of evaporation, because the two process comes one. The two process comes one. The changing of solid into liquid, changing of liquid into gas comes one, and heat of sublimation is the result of the two. Is the result of the two. So, and don't forget, sublimation is what? It is endothermic process. It's endothermic process.
So if sublimation is higher than heat of vaporization,
Yes.
evaporization is higher than heat of fusion.
Yes, we can say so. And we have deposition. What is deposition? Just like we have condensation, changing the gas into liquid, we have deposition, changing the gas into solid, without having the liquid phase. Without having the liquid phase. We call them deposition. The amount of heat, what is the system? Is deposition is exothermic or endothermic? It's exothermic. Exothermic. And how much heat is needed for deposition compared to how much it is needed for sublimation? But they are the same. They are the same in number, but they are opposite. Okay, but 100 degree, by the way, is a boiling point of water. 100 degree is not sublimation. Okay? Yeah. It's going to be that. Yeah, it's going to be that. But 100, exactly 100 is starting the boiling point. It starts. We see molecules that bubbles out.
Also above 100 is
Evaporation.
and then under 0 degrees
Yes. I don't want you to get confusion with the boiling point and the energy that is needed to apply there. Okay? These are two things. Energy is measured in what? In what unit energy is measured? Energy is measured in joules or calories, right? Kilojoules, okay. These are measurements of energy. Temperature is measured in Celsius, in Kelvin, in Fahrenheit. Okay? Now, I don't know, because see, I don't want to go further. Let me see if we have it on the slide. If we don't have it on the slide, I'm not going to say it. We can just keep. Let me see something here. Well, okay. Okay, let me. Oh, very good. Okay, we're done. Okay, let's see the heating and the cooling curves here. Are you familiar with the formula? Are you familiar with the formula mass times specific heat times difference in temperature? This is a formula that can be calculated, heat lost or heat gained, very good, by a substance. Equals to heat lost or heat gained by substance equals to mass times specific heat times difference in temperature. I can write mass M. I can write specific heat as C. I can write difference in temperature in delta T. And I can summarize this MC delta T equals to Q. Okay, thank you very much. I can see. Q equals to MC delta T.
What does that say? Heat of what?
Heat lost or heat gained by a substance can be calculated as mass, which is M, times specific heat of that material, which is C. Difference in temperature, which is delta T. Well, the reason why I bring this issue is that the amount of heat that is needed to change a liquid into solid, a solid into a liquid, or the amount of heat that's needed to change a liquid into a gas is measured by this formula right here. The temperature is measured by the thermometer, okay, but the heat, the energy that is required to change the substance is measured by this formula, and this is the basic principle for the calorimeter. Calorimeter is an instrument used to measure how much heat is needed or how much is applied to change a solid into a liquid, or what is the calorie value of the food. Calorie value is the nutritional value of the food. How much energy is needed? I eat chips, and if I eat chips, like it gives me 60 kilojoules or 60 calorie whatever, right? That is measured by calorimeter, and it is based on this formula here. It's not measured by thermometer. Thermometer tells me how cold or how hot the substance is. Okay, now think about this, and let's go here. Now, this is a heating curve. A heating curve shows how the temperature of substance plotted on the vertical axis. Okay, we have assumed that we have temperature here on the vertical axis changes as heat is added. You are adding heat versus temperature. Okay, now at point A, now let's assume this is water, right? What is the status of water at point A? But it is solid. It should be below zero. Okay? It should be below zero. It's because if you say zero, still at this point it is no, it is solid. Minus 32, minus something. Let's start with minus 25.
Okay.
I go up. I can't write here, that's much good. Minus 25 here. Minus 20 here. 0 here. Can you see? Okay, well, but I'm okay. Let's assume minus 25 here. Minus 10 here. You can write it in your paper. I'm telling you, you write it, okay? Minus 25, write minus 10 here. Write 0 here. Just draw this picture on your paper. Kayla, draw this. Okay? Now, yes, start with minus 25, minus 10, 0. Write 100 here. 100 here. Okay? Okay, I'm going to ask you to write 125 here. Okay, draw this picture. What is this one? Minus 25, minus 10, 0. Okay, between 100, write 80. Write 80. What's happening here? If you move from minus 25, what did I tell you? Minus 10. What is the status of water? Solid. Up to here. Starting to melting, right? Now, you see the straight line? In mathematics, a straight line is called what? When you do mathematics, when you do your geometry, what's a straight line represents? Straight line is constant, right? Temperature remains constant, right? There is no temperature change. What does that mean? Equilibrium, no. In concept, you're right, but it's not equilibrium exactly. What is this point BC refers to? Just what you, the chemistry, what you learn right now. In other words, is it heat of fusion or is it heat of vaporization? Heat of fusion. Point BC is heat of fusion. In heat of fusion, there is no change in temperature. The temperature remains constant. How do I know? The graph. The graph is constant. It's a straight line. There is no change in temperature. Okay, so what? The temperature remains constant at 0 degrees centigrade, something going on, which means that from B to C is solid changes to liquid, and it continues. It continues. It goes on, up to C. Up to C, the whole solid is changing into a liquid. Now you don't see liquid, you don't see solid here. You see liquid. Now from this, it starts to get up. When it starts, it's liquid now. There's no more solid, right? What is the status of the water here? I know. It is status of liquid or solid? It's a liquid. Here, liquid. Here, liquid. Here, liquid. You get here. It starts to boil. Now again, what was the temperature here? 100 degrees centigrade, right?
Yes.
The temperature remains constant. What does this table tell you? What does this line, this segment tells you? Heat of vaporization. HV, yes. Heat of vaporization. That is, from D to E, yes. Heat of vaporization, HV. Heat of vaporization. Heat of vaporization starts here, completes here. Now every single molecules of water is changing into gas. And it boils now. Okay? So really, we can say a lot of things here. The process here, is it endothermic or exothermic? Yes, the process here in solid between B and C. You know, I may have asked you, I may choose a graph like this, and I may ask you, what is the line segment BC refers to? Exothermic. This is liquid here. I mean, this is solid here. And then it turns into a liquid. You have to apply energy here, endothermic. Is the temperature is changing here?
No.
The temperature is not changing here. Now,
No, temperature is changing, heat is not changing.
the temperature remains constant now. The temperature remains constant. This
Is
is,
this heat?
what is the temperature here?
0.
0 degree centigrade. What is the temperature here? What is the temperature here? It's a straight line. The temperature remains constant. The temperature is not changing.
This is temperature. The horizontal line is not.
The horizontal line tells you the status. They're like solid, liquid, gas.
Oh,
Okay?
yeah.
Okay? Now, another issue that I would like to bring is, do we understand this up to this point? Okay. Now, here is another question that we raise here, that we raise. How much energy is needed to bring from A to B? Okay? How much energy is needed? Now, you have to think about this formula right here. MC delta T. Now, let's say that we start with, I can pick an example. I can give you an example. 20 grams of ice. Write down, 20 grams of ice. Okay? So, here is my question for you. If you have 20 grams of ice, to bring the 20 grams of ice from A to B, how much energy is needed in joules? The specific heat I'll give you, the specific heat for water is known. It's 4.18 joules per gram. Okay, let me right here. I'm sorry? The energy. Calculate the amount of energy needed the amount of energy needed to raise, what did I say, 20 grams of ice, right? 20 grams of ice, 20 grams of ice from point A to point B. okay, how much energy is needed to raise 20 grams of ice from point A to point B. Specific heat of ice is 4.184 joules per gram degree centigrade. Mass of the ice is 20 grams. I'm sorry? Yes. Joule per gram degree centigrade, yeah. Yeah. Okay. 4.18 times the difference in temperature.
What's the difference in temperature?
The difference in temperature. At this point, what is the temperature of A? Minus 20. What is minus 25? Okay, did I tell you minus 25? What is the temperature here? So the difference is 0 minus 25. The temperature difference is going to be T final minus T initial, right?
Okay, so it's negative 2009.
Well, the difference in temperature means final temperature minus initial temperature. Delta T is going to be T final minus T initial. The final temperature is 0 minus the initial temperature is minus 25. That is 25. Positive.
2009.
How much? So heat is mass. This mass is 20 grams times 4.184 joules times 25 degrees centigrade. Okay? So that gives you what? 2090? 2090?
Yes.
2090 what? Joules of energy. Does that make sense? If it's not clear, please ask, okay? That means you need to have 2090 joules of energy to bring a 25 grams of ice into 0 degree grams of ice. How much energy needed? 2090 joules energy is required. How much? 2090 joules. Is it endothermic or exothermic? Endothermic. Endothermic. Is class is clear, everybody? Okay? Now, in fact, to bring the whole energy to change from A to this point, the last point, it's going to be the amount of energy is going to be this segment plus this segment plus this segment plus this segment plus this segment. Everything has to be added together. It's going to be higher, of course. It's going to be the highest. Yes, ma'am. It is the specific heat of water. The specific heat is a constant number, okay? If it was oil or if it was something else, the specific heat value will be given to you. If it is sand or aluminum, copper, every material has their own specific heat capacity, C, okay? What is specific heat? What is it? It is the amount of substance that is used to know how much heat that substance can absorb. Water absorbs 4.184 joules of energy per gram. Other substances may absorb less. That's the nature. That's the nature of the substance. So this is given to you actually. You don't have to memorize this. Okay? But now the idea is here. We're going to compare. The heat is calculated by this formula. The heat loss or the heat gain. Temperature is calculated by what? By using thermometer. Okay? This idea, which is heat loss or heat gain, is a reflection of calorimeter, which you're going to do in experiment in calorimeter. Calorimeter is based on this principle right here. So that's calorimeter. That is, say for example, in one of the experiments that we have to do in the lab will be, I'm just giving you a general idea. Say for example, you have a cup here. Okay? In this cup, you have water. You boil the water, right? And you put a metal copper metal, for example, a copper metal, okay? You put that here. And then here you have a cool water. Once you boil the water inside the copper, okay, you take this hot copper and quickly put it here in cold water. Now, what's happening generally? Tell me what's happening. It's heating the water. The cold water is going to work. Okay, let's say the cold water initial temperature was 20 degrees centigrade. After you put the copper, its final temperature will be 27 degrees centigrade. It's going to definitely, it's going to be raising. Temperature will be up. By how many degrees centigrade? By 7 degrees centigrade. Now the question is this. The question is, how much energy, how much heat is needed to raise a 20 degrees centigrade water into 27 degrees centigrade? How much is needed? You see, that's how the law of conservation of energy here. So what you can do is, there are two things that are happening here. Heat lost by the metal, right, equals to heat gained by what? By the other water, by the cold water. Okay? But the idea is we have to make sure that it has to be the same. That's why we use calorimeter. That's why we use a cup, styrofoam cup or something. The transferring has to be very quick. And then make sure that you have to cover the entire part so that all the heat that was from copper has to be exactly transferred into the cold water without any losing. Well, we try our best sometimes, but sometimes it doesn't work. Yes. There's always loose. You have to be very careful. I mean, you can't eliminate the mistakes, but you can avoid some errors anyway. Okay. So the idea is there is heat lost by the metal, is heat gained by the cold water. Okay. Sometimes, how much heat is lost by the metal can be calculated as mass times specific heat of the metal times the difference in temperature. How much heat gained by the cold water, mass times specific heat of the water times the change in temperature. These are the formulas that we're going to use. Okay? The whole concept behind this is what? It is the law of conservation of energy. The law of conservation of energy. The law of conservation of energy tells you that the heat lost by the metal, the hot metal, has to be equal to the heat gained by the cold water, regardless of some losing. Okay? So you make sure that that's why you have styrofoam cup, you have the cover that cover the top of the cup to avoid any loss. And we are assuming that the hot copper has to be transferred into the cold water. During the transferring process here, nothing is lost. Okay, so the heat loss equals to the heat gain.
What's that, CM?
Cm refers to the specific heat of the metal. And then this is called mass times the specific heat of the water and changing temperature. Okay? Yes? Well, I mean, there is also, this is the principle, but there is of course, there's a calculation here. Okay? You need to know, you have to measure the weight of the mass of the copper or the aluminum, whatever it is. And the specific heat of the metal will be given to you. Huh? It will be given to you. And at the end, actually the goal is here. By calculating, here is the thing, here is the beauty of this. By calculating the specific heat of the metal, okay, by calculating the specific heat of the metal, if you know what is the specific heat of the metal, you can tell what is that metal. Is the metal is copper, aluminum, zinc, whatever, iron, because every metal have their own specific heat capacities.
So Professor, the specific heat capacity will be given, right?
In the experiment, maybe one of the questions that you'll be asked is to find the specific heat of the metal and thereby find the metal, identify the metal. Yes.
Okay, so the mass is the weight of the copper, the specific heat, so we're going to boil the water and then we're going to
On the metal.
and then we're going to take the thermometer and check what the copper is, what the heat is of the copper.
Yes.
So we're going to put it on the copper.
Yes.
And then the difference in temperature is the cold minus the
hot. Yes.
Right?
Yes.
Okay.
Yes. And then the whole idea is everything. The mass of the metal. The difference in temperature. The specific heat of water. You measure the difference in temperature by the thermometer. One thing that you don't know is this, the specific heat of the metal. Once you don't know the specific heat of the metal, you calculate that, you get a number. Once you have that number, go to Google or go to the book or something and find out the numbers. And if that number matches with the metals that you're looking for, so the metals that you put inside the cup is going to be maybe copper or aluminum or zinc or whatever. That is the identification. One way we can identify elements is by using their specific heat capacities. Specific heat capacity, like for example, if I have a liquid and the specific heat capacity of a liquid is 4.184, then what is that liquid would be? Water. Yes. If I have 0.8 something specific heat capacity, can it be water? No, it can be something else. I don't know what, but it can be something else. I have to look, I have to make a Google search or whatever, and then find out. Because every material has their own specific heat capacities. It's not like you don't have two materials that have two specific heat capacities. So, I don't know what's happening here.
Well, this is over with anyway.
Okay, we are getting into, okay, we are in 20, this is 26 and this is 27, okay. The difference in 26 and 27 is that in 26, all the process is endothermic process, okay? On 27, all the process is what? Exothermic. From gases, from vapor, we change into a solid. So we have condensation, we have freezing. Remember, here we have melting and boiling. Here we have freezing and condensation. But the amount of heat remains the same. The only thing is they are moving to the opposite directions. Okay? This chapter is over.